Hi there, I'm Alan Evora with Affinity Energy. This afternoon, I'm going to talk to you a little bit about high availability and redundancy in control systems. So why is this important? Well, in the world that we work within, which is mission critical facilities, we often see a lot of misinformation and a lot of underspecification when it comes to high availability and control systems. Some of this is due to the misconception that high availability is expensive, as well as the understanding or the misbelief that high availability systems are overly complicated. So we're going to debunk that myth this afternoon and talk to you a little bit about some of the things that owners should know about high availability and redundancy. So before we jump right in, a little bit about Affinity Energy. We're a specialty control systems integrator. We specialize in mission-critical facilities and distributed generation facilities. So for us, that's primarily data centers and hospitals, airports, as well as utility-scale solar farms and landfill gas-to-energy systems. Our expertise is around SCADA and electrical power management systems, sometimes referred to as EPMS, programmable logic controllers, and submetering. Lastly, we are a Schneider Electric critical power eco-expert. That means we maintain certain expertise on Schneider Electric products, and we are able to help customers who are seeking out a more advanced solution using those products and services. And although we are a Schneider Electric critical power eco-expert, we do maintain an open systems mentality and recognize that every solution requires a unique design and application. So let's get started. First, I'd like to talk a little bit about programmable logic controllers. So typically in the systems that we work with, we use programmable logic controllers as our main control engine. So this means that it interprets all of the sensors as well as it controls all of the actuators and valves and perhaps even the electrical switchgear. What we're striving for when we design a high availability system is to eliminate single points of failure. What this typically means for us is that if you have a single programmable logic controller, if it fails, there should be a mechanism by which the process or perhaps the equipment will continue to operate even though the primary controller has failed. So where might we see this type of need in the industry? Well, typically it's going to be wherever there might be significant impact to facility. Perhaps it might impact life safety, or it might have significant repercussions in terms of production or even efficiency. So example, in most hospitals, there's a requirement that says when there's a loss of normal power, a generator must supply power to the loads within 10 seconds. Well, if you only have a single programmable logic controller responsible for ensuring that power delivery, then the ability to provide power within that specified time frame would be jeopardized. So having a redundant controller would certainly be important in that type of application. When we talk about redundancy, there's actually a couple different categories of redundancy, and I'd like to review those with you. The first one is actually referred to as cold redundancy, and really this is a situation where you are probably going to have a control system, and instead of having something that would be online and there would be some type of effective or timely switchover, you've probably got some spare parts or you've got some ability in order to respond upon failure of the primary equipment and put into service equipment that you've got on the shelf. This equipment may not necessarily be pre-programmed. It may not even be necessarily ready to put into service. It may require a little bit of human intervention. But again, it beats not having any spares or having any mechanism in order to recover at all. And depending on your situation and the type of process or the type of facility, this type of redundancy may be warranted. The second type of redundancy is what we refer to as warm redundancy. So this takes it a little bit further. You will have, again, equipment that will be duplicate to your primary equipment, and that equipment will most likely be pre-programmed and ready to be put into service, by perhaps just switching on or moving a couple cables, but certainly it's going to be a lot faster than cold redundancy, but not as quick as if it were done automatically as part of the system itself. So a lot of times we refer to this as warm redundancy. For example, with a SCADA system, you might have a primary computer that runs your SCADA system, and then perhaps in that same room you might have a second computer that is always configured with the up-to-date configuration. And if the primary computer were ever to fail, it's just a matter of turning on the new computer, perhaps moving some of the network cables, video cables, or peripherals, and then you're back up and running. And certainly this could be a potential cost-effective way to provide some level of redundancy depending on your application. The third type of redundancy, which is the primary subject for today's webinar, is what we refer to as hot redundancy. And in this type of redundancy, everything is automatic, meaning that you'll typically have controllers or you'll have automation in place such that if the primary controller or the control mechanism fails, the secondary control mechanism or controller will take over, and it will be seamless, or it will be not noticed by the equipment or the process. So another word that's typically used for this type of redundancy is bumpless, because what's happening in this type of situation is you have a primary and a backup controller that are essentially what we call in lockstep. And essentially they're monitoring the statuses of one another, and upon failure of one, the other one automatically takes over. And this typically happens within what we call the program cycle of the controller. So it's very fast. Again, we talked about situations like hospitals or healthcare where human life or life safety could be a factor. We certainly see the need within data centers where there are financial transactions which could be worth millions, billions of dollars, and therefore a computer system or any important system that were to become compromised would have a significant financial impact. We also see certain manufacturing processes that certainly require redundancy because the failure of the control system would lead to waste, it might lead to non-productivity, and also have a significant impact. Could even have some safety repercussions depending on the type of process. So again, there are many situations where having redundancy, and specifically high availability type redundancy, is warranted. What we're starting to see, or what we've been seeing probably within the last 5 to 10 years, is a significant increase in the availability of redundant solutions. So pretty much all of the major PLC manufacturers now have redundant solutions, and these redundant solutions aren't necessarily just limited to their highest end controllers. We're actually seeing controllers now that I would consider to be in the mid-range that have this type of capability. And we're also seeing one of the trends, in addition to availability, is the cost has substantially come down. And with that cost, meaning the hardware and the soft costs, we've seen the configuration, the amount of time or the investment in configuring redundancy come down as well. So it's a win-win really for all those who are in need of a high availability system. I wanted to give you an example. We recently looked at a small data center that had already installed a non-redundant control system. That control system was based on what I refer to as DDC, direct digital control, or some people might refer to that as building automation. It tends to be more of a commercial type product. This particular customer used a DDC-based control system to control their HVAC system, and specifically the chilled water distribution at the data center. They had or experienced significant downtime as a result of not having a redundant solution, and had asked us to come in and take a look at what it would take to possibly upgrade or retrofit that control system. Based on, again, it was a small data center, less than 20,000 square feet, but looking at the existing DDC system, which was about an investment somewhere in the 10 to 17K. Again, we weren't the original installer, so I don't know the exact price. I just know based on the research that we did. A PLC-based redundant solution would have been about $35,000. So certainly it's going to be a little bit more expensive, but at the end of the day, as an owner, you have to determine what the cost of downtime is worth to you. Is the extra $17,000 worth it to avoid downtime and potentially lose customers, or perhaps even more importantly, customers who lose data? When it comes to assessing your needs for high availability, it's important to understand, again, not only understanding the impact of downtime, but really determining what your goal is. Here's an example that I'd like to share with you on a rating system that's developed by the Uptime Institute. The Uptime Institute has come up with a classification system as a means to effectively evaluate data center infrastructure in terms of business requirements for system availability. And typically the way it works is they're looking at Tier 1 as being a basic non-redundant system all the way up to Tier 4. And sometimes they talk about this redundancy in terms of the level of nines of availability. And nines being, again, 99.995% availability would be considered 4 nines of availability. So as we move from Tier 1 to Tier 4, you can see that at Tier 1 we have 2 nines of uptime and essentially no redundancy required. And we can have up to 28.8 hours of downtime within a year. And then we move all the way from Tier 4, which has 4 nines of uptime, but we're moving from 28.8 hours of downtime all the way to 26.3 minutes of downtime. And then not only that, in these types of systems, the number of hours of power protection, similar to, say, your UPS on your desk, increases, meaning that in a Tier 4 system, they can operate for up to 96 hours, or essentially 4 days, before they run out of UPS power. So again, understanding your requirements and the goals that you're trying to achieve within your facility are a good way to determine what systems and what level of availability or redundancy you should have. Up to now, we've primarily talked about the controls portion of a facility or of a system. But the controls only make up a portion of the overall system. So let's talk a little bit about each of the different components that might make up a control system within a facility. The first is obviously the controller itself, or the programmable logic controller, PLC. As you can see, I've kind of presented a typical topology. And this is an example that I took from a recent Schneider Electric instruction manual on building a redundant architecture. And this is typical of other manufacturers such as General Electric, such as Allen Bradley, as well as Siemens. You typically have 1 or more controllers, but typically 2 controllers. And then those controllers do not contain what we call any I/O modules or input-output modules. They are strictly in place to execute the control logic for the overall system. But then those controllers are linked to remote or I/O, input-output modules, that reside outside of the primary racks. And you can distribute that I/O throughout your facility depending on where the equipment is. You can distribute it in a way that reduces the amount of cabling that you have to pull within your facilities. But again, there's a lot of flexibility in terms of that design. A couple other things to note is that those controllers, by this dashed line, they're linked by a cable which is allows each of those controllers to determine the status of the other. So again, only one will be in control, but the other one will be sitting and waiting to take over control should should the other present a fault or a failure. And then there's a ring. You can see the dark line that goes around to all of the I/O that forms a ring. And that ring is a distributed network that connects all of the I/O back to the controllers. And typically that ring is configured in a way that allows some redundancy within the network itself. And we're going to talk about that shortly. Probably the primary difference between a non-redundant and a redundant architecture is the presence of a second CPU. Again, if you may not have a less investment in a network, but it's not a lot to add a second CPU to the architecture given the same amount of I/O. When we talk about designing a control system, you have your instruments as well. Your instruments are basically what provide the feedback to your controller. So just like in order to control, say, temperature within a room, you might have some temperature sensors. They could be thermostats, or they can be thermistors, or they can be RTDs. And if control of temperature within that room is very critical, you may want to consider not only having one temperature sensor, but maybe having several temperature sensors. So certainly you have to consider your application, and you have to consider what would happen should one of the instruments that's critical towards the control of the process or the equipment or some aspect of the facility, should it fail, what you would do. And that applies not only to instruments, but also controls that are outside of the primary control system itself, such as it could be motors or pumps or fans, or it could even be electrical switchgear. It could be UPS systems. Again, whatever it is that comprises your control system, you must take into consideration from a holistic view what it is you're trying to achieve at the end of the day, and identify those single points of failure. As I commented earlier, we talked a little bit about the network, and in that architecture or topology that I displayed, we showed a ring, and a ring that basically went between the primary, secondary, and all of the remote I/O modules. Well, typically what you want to do when you design a network is you'd like to also provide the capability that in the event of a failure in any of those segments of the network, that network will still continue to operate. So typically we'll see the use of what we call a self-healing ring. And that technology has been around for many years. There are many manufacturers who have created their own version of it using the rapid spanning tree protocol. But again, if you're going to go to the expense or the investment of designing a control system, you need to make sure that you pay attention to all the components, and the network is certainly one of those. I'd like to also expand on, when we talk about networks, one of the things that you'll hear, or that is often discussed when we talk about redundancy or even remote I/O, is we talk about non-deterministic versus deterministic networks. So a non-deterministic network would be, for example, Ethernet TCP/IP, or what most people are familiar with from their homes or their workplaces, where again you go to search the web, or you go to maybe perform some action on the internet, and you get some response. Typically that response, though, is not guaranteed. That response happens within some time frame, and it really just depends on what's happening on the network. If two people issue a command at the same time, there could be a collision on the network, and there's a reset, and then there's a random timeout period. And so, but within control systems, we can't develop high availability systems based on randomness. And we need consistency, and we also need, again, to understand when we design these systems, when we issue a command from one controller, we need to know it's not only the command coming out of the controller, it travels over the network, it's recognized in the distributed I/O module, and then an action is taken to control a motor or in the case of a command or an output being issued, or vice versa, where you're reading a temperature and then making a decision. So there's network latency, there's going to be the reaction times of all of the components that are within that data acquisition or command stream. So you'll hear the term deterministic networks, and that just means that the way that network, the characteristic of that network is such that the timing is well understood based on the design and the configuration and the protocol. So most of the redundant architectures use a deterministic network. For example, Allen Bradley and Schneider Electric use what's called Ethernet IP, and GE and Siemens use Profinet. But just again, be aware that if you look at a solution and you're told that the distributed I/O network is using something that's non-deterministic, that should throw up a caution flag for you to ask more questions. The control system itself and the networks and the instruments certainly make up the majority of the control system, but the SCADA system is probably the tool that's used to visualize what's happening within the control system, to manage at a high level or a supervisory level the set points, to be able to perhaps respond to alarms and determine should a change in the way that the control system would operate it is needed. So it's really the SCADA system, which stands for Supervisory Control and Data Acquisition, performs multiple functions. It's the HMI for the operator, it's also the historian for data logging, and also the mechanism that would alert you to the status of your high availability system. So if it's important to you that operators have visibility to your control systems at all times and have the ability to interact with their control system, you may want to consider specifying a SCADA system that is also redundant. And redundancy within SCADA systems is also something that has matured substantially, and there are cost-effective solutions out there. We like to use one by VT SCADA, but I do know that all the major manufacturers have redundant SCADA solutions. Lastly, I want to talk a little bit about something that doesn't necessarily comprise your control system in terms of hardware, software, but is very important when it comes to high availability, and that's system commissioning. Commissioning is the formal process of going through and doing point-to-point checkouts to test the functionality of all of the components, as well as test the operability of the sequence that was designed into the control system, or sequences if there are multiple control sequences that are part of the control system. It's been historically, I would say prior to 5 or maybe even 10 years ago, commissioning was done, I would say, on a lot of facilities in an informal manner. Sometimes it was performed by the system integrator itself, or it might be something that was overseen by the design engineer. Nowadays, most mission-critical facilities typically employ a third-party commissioning agent or a separate party who wasn't involved in the design nor in the development and installation of the control system. They'll have no inherent biases, and therefore they have also, in not being familiar with the design, they are there strictly just to put that system through its paces and provide the owner with peace of mind that should this system be called upon to function under one of the failure modes, that it will do its job and it will do it properly. For example, we recently upgraded a SCADA system on an emergency power supply system for a data center here in Charlotte. And that particular control system, even though we were upgrading the SCADA system, it did have a redundant PLC. As we went through the process of recommissioning the SCADA system, the owner took the opportunity to do a complete test of the redundancy. And what that meant was, in addition to going through a series of tests to identify the operating modes and the failure modes of, say, the generators, or maybe even some of the other components such as the transfer switches, they did a full pull the plug test where they simulated the loss of utility power to the building, and then seeing that the emergency generators came online, and that in the process of coming online they even failed the primary controller, so they could witness themselves that emergency power was provided to the load within the required time frame, and that should this situation where primary controls fails, they walked away confident that they had a system that would provide them with the ride-through capability from the generators and then ultimately the UPSs to allow the computing resources in that financial data center to continue to operate. So again, be careful that when you specify a control system that you also make sure that you invest the time to commission that system properly. So in conclusion, I'd like to talk about a couple of summary items with respect to high availability and redundancy. One of the things that was mentioned in an earlier slide is that, again, the cost of high availability and redundant systems has come down substantially. They are certainly still going to be more expensive than a non-redundant solution or a system that might utilize warm redundancy or cold redundancy. However, again, I can't emphasize enough how important it is to understand what is the cost of downtime within your organization or your process or your piece of equipment. It's been my experience that most people don't understand the cost of downtime until they experience it for the first time. And at that point in time, no amount of money, or the amount of money that they've experienced, would more than have paid for, or certainly if invested on the front end, would have been a worthwhile investment. But at that point, it's too late. At least too late in terms of they're going to pay more for upgrading that system after the fact than you would have had it been specified in the beginning. And so once you understand what downtime is or how that might impact your organization, it will allow you to consciously determine what level of availability makes sense for your organization, and also determine what your strategy is going to be in order to meet that. Sometimes we've found that high availability systems also aren't necessarily in the domain of just the owner itself. I'll give you a good example. We recently had a central utility plant which was built by an energy services company who was going to be providing both emergency power, chilled water, compressed air, as well as other types of utilities to a high-performance manufacturing facility. Within that contract that the high-performance manufacturing facility had with the energy services provider were penalties and liquidated damages that would result from disruptions of service. The party responsible for running the central utility plant wasn't necessarily the benefactor of what was produced by that utility plant, and it's primarily the energy services company who is ultimately responsible. And so, again, it's not just owners, but it's anybody within the delivery stream or that would impact the service or the equipment or the process that's involved. You also want to make sure that when you're designing your systems that you take a holistic view. So don't get blinders on and think you're solving your problem by putting in a redundant PLC only to leave instruments or networks or even your SCADA system vulnerable. So even if you design a redundant PLC but then have a network that has a single point of failure, you may find that your investment in that redundant PLC is somewhat diluted. And lastly, we find that knowledge over high availability and redundancy sometimes is not within the domain of the engineering firms that are doing the mechanical, electrical, and plumbing design. In that case, I would encourage owners to either have their engineering firm engage a control system integrator, or the owner can engage a control system integrator directly in order to help guide and specify the types of systems that need to be in their facilities. So thank you for spending time with me. I hope you've been able to learn more about high availability and redundant systems. As you can see, there is no mystery or myth about high availability systems. There's certainly a wide array of options of PLCs, SCADA systems, networks, as well as instruments available to design a system that meets your uptime requirements and helps you to operate your facility in an efficient, safe, and reliable manner. And remember, should you have any questions, we're here for you. We're a control system integrator that specializes in mission critical power. Therefore, we've designed many redundant and high availability control systems. Give us a call. I'm Alan Evora with Affinity Energy, and thank you for attending this webinar.